Okay, we're going to dive into Chapter 8 now. And Chapter 8 is all about formulas and proportions and variation. Okay, so what's a formula? A formula is just an equation that means something. Okay, it means something. 2x plus 3 equals 12 didn't mean anything. We solved that equation to practice our skills, learn the techniques, okay? A formula relates something in the world. Now, some formulas are derived from, laws of physics, and there's relationships between things that are just well known and understood, and the formula gives us a mathematical way to explain them. Other formulas are created from what's called empirical data. Something was observed and this data was recorded, and it was noticed that one thing affects another thing, and then there's an attempt to mathematically explain that data by turning it into a formula. Okay, we're not concerned so much with where these formulas came from. We're just going to play around with them a little bit here in this section. What we're going to do here is evaluate. Formulas, okay? Evaluate them. Okay, you're gonna see there's gonna be multiple letters of the alphabet involved, right? We're used to only having one, just good old X, or maybe we switch to Y or Z or some other letter. You're gonna see formulas have multiple letters. But in order to evaluate them, we will be told what all except for one of those letters are, and then we're gonna plug the numbers in and evaluate the formula. All right, example 1 on page 378. Talks about engine efficiency. We're given this formula, E equals I minus P over I. Engine efficiency is calculated by taking the input, in this case the input energy or heat, minus the output energy or heat, and dividing it by the input. Okay? So, think about it. If you put some energy into the engine of your car, let's say, and all of that energy went into, making the car go, then you would have no output heat, and you would have no losses. This P would be 0, and you would just have I divided by I, which is 1, and 1 as a percentage would be 100%. Okay, efficiencies are always shown in percentages. So you have a 100% efficient engine, which is not possible. Okay, what happens in real life? The engine gets hot. It needs a radiator to dissipate that heat and throw the heat away. So we're going to quantify that. The input heat versus the output heat. Okay? In an example we're given here, we're told that I, the input heat, is 24,000. The unit is calories. Okay? It's a metric unit of heat or energy. And we're told that the output heat, P, is 8,600 calories. Okay, so let's calculate this efficiency. 24,000 calories minus 8,600 calories, and then we're going to divide it by 24,000 calories. Let's think about the units for a minute. Adding and subtracting requires us to have the same unit, right? If we try to add 12 feet and 3 inches, we couldn't do that, right? We had to convert them all to the same unit. Well, we have the same unit of calories, so we're good to go there. So I'm confident that subtraction makes sense, so I'm going to take 24,000 calories minus the 8,600 calories. I'm going to get 15,400 calories. Divided by 24,000 calories. Well, now I'm dividing units. What happens there? Those units are going to cancel away. So my result is not going to have a unit, and that's correct. Efficiencies don't have a unit. You see, I'm going to get some decimal. 15,400 divided by 24,000, I'm going to get 0.641666, and the 6 repeats, right? So your calculator will eventually throw a 7 at the end, probably. That's a repeating 6. Now the instructions, I don't think I read that, says round to the nearest thousands. Okay, so tenths, hundredths, thousands. We're going to round right there to that position. So I look to the right, it's 5 or greater, so I'm going to call that 0.642. 2. That's the efficiency of my engine. Okay, now efficiencies are almost always reported as a percentage. So how do I turn that decimal to a percent? It would be 64.2%. Okay, is that a good number? I don't know. I don't know much about engine efficiencies. I don't even know what kind of engine we're talking about here. I mean, 64.2 doesn't sound that impressive, you know. A 100% efficient engine is a theoretical, great engine. There's no such thing, but 100% is great. How good is 64? I don't know. Maybe that is a good number, okay? But that's the efficiency of our engine here in this example, okay? Units make sense. Everything makes sense. There we go. All right, we have evaluated that formula. Let's check out another formula. Example 2 goes back into circuit resistance. Okay, we're given some formula to calculate total resistance. So I've got R with a subscript here. We haven't seen too many subscripts in our course. A subscript is a label. Okay, it's not a mathematical operation the way an exponent is. An exponent or power, we know what to do there. A subscript is just a label. That's T for total. That's the total resistance equals. What does it equal? Resistance number 1 times resistance number 2, and then divided by resistance number 1 plus resistance number 2. Okay, again, we're not really concerned about where that formula came from. That's the formula given to us. We're asked to evaluate and calculate the total resistance. Well, I've got 3 unknowns there, RT, R1, and R2. In order for me to come up to a value here, I need to be told 2 out of those 3. And in this case, I'm told R1 equals 10. The unit of resistance is ohm. It's the Greek letter omega, 10 ohms. And I'm also told what R2 is. R2 is 6 ohms. Okay? The rest is up to me. How do I find the total resistance? RT. Well, I'm going to take 10 ohms times 6 ohms on the top in my numerator, and I'm going to take that 10 ohms plus 6 ohms on the denominator. Okay, let's think about what's going to happen with units here. Well, 10 times 6 is 60. Okay. Ohms times ohms gives me square ohms, right? Okay. On the bottom, I'm adding, so I must have a common unit, and I do. So 10 ohms plus 6 ohms gives me 16 ohms. All right, so far so good. So I need to take 60 divided by 16. Okay, that's some number. We can figure out what that is. It's going to be the decimal 3.75. But what happens to my units of ohms squared divided by ohms? Well, remember what ohms squared means. It means ohm times ohm. That's ohm squared. Divided by ohm. So one set of ohms is going to cancel away, and there's going to be 1 ohm left. So my answer has a unit of ohm in it. Does that make sense to me? Yes, it does. Because I'm calculating a resistance. Resistance has the measurement of ohm, the unit of ohm. So yeah, that does make sense to me. If all the units somehow disappeared, I might start questioning my formula and say, wait a minute, I should have an ohm left on the board, and I don't. Okay? Previous example, we had no unit left, right? And that made sense there. Efficiency doesn't have a unit. Resistance does. All right. I think we're doing good here. Example 3. We've seen this formula before, but there's a little bit of a twist here. Perimeter of a rectangle. Okay? Twice we said 2L plus 2W, probably the first time we introduced it. Then we learned about factoring. We said we can factor a 2 out of there and call that L plus W. Okay? So, P equals 2 times L plus W. That's the formula we're going to work with. It's the perimeter of a rectangle. Now, if I wanted you to calculate the perimeter, I would have to give you the length and the width, right? There's 3 unknowns on the board. I'd have to give you 2 of the 3. Well, guess what? I'm going to trick it up a little bit. I'm going to tell you what P is. P equals 12 feet. And I'm going to tell you what L is. L equals 4 feet. You see? And I want you to find W. So it's not quite as straightforward as it may seem. Right? Well, let's plug in the information. P equals 12. And I'm going to drop the units here. Let's analyze the units for a minute. Length and width are both going to have unit of feet, so that makes sense. Perimeter has units of feet. 2 has no units, so feet equals feet. That makes sense. So we're going to drop the unit here. So 12 equals 2 times L is 4. W, I don't know. I got to call it W. That's what I'm looking for, W. Okay, now we can handle this equation. A minute ago it seemed like it was hard, but now that the numbers are there, we've seen equations like that before. Solve for W. How do you do it? Let's distribute our 2 across. We'll get 8 plus 2W. Okay, subtract 8 from both sides. Subtract 8. I'm going to get 4 equals 2W. Divide by 2. Divide by 2. I'm going to get 2 equals W. Right? And of course I could turn that around and say W equals 2. Okay? I'll go ahead and sneak the units in now. We know the units worked out, so the unit is feet. W equals 2 feet. Okay? This formula was not set up to find W easily, right? We had to do all this little algebra. Well, in a little while, later on in the next video, we're going to do the same thing, except I won't give us any numbers. We're going to keep the symbols in there, and we're going to shuffle this whole equation around, this formula around, and we're going to get W equals a bunch of stuff over here. Okay? Bunch of letters, no numbers. It'll just be a shuffling around of this formula and making it look different. Instead of P equals all that stuff, we're going to have W equals all that stuff. Okay? And then we could have, at that point, plugged in the information and found W. So we're going to practice our formula shuffling in the next video. Okay, right now we're just doing some more evaluating. Let's check out example 4. Okay, page 379. Okay, we've seen this formula before. Simple interest, I equals PRT. What's the relationship between PRT? 3 things multiplied together, right? Interest, simple interest equals the principal P times the interest rate R times the time T. Okay, we're given some information here. We are told what? We're told I. So again, the equations, the formula is not really set up perfectly for us, because P is going to be our unknown, not I. Okay, it's set up right now for I to be the unknown, but that's just how the cookie crumbles. It wasn't given to us that way. We want to know, we want to earn $94.50. Okay, that's what we want. And the question is going to be, how much money do we need to invest in this account in order to earn that interest? So I want to earn $94.50. My rate, yeah, right, is 21%. Good luck finding that, right? Now again, interest rates really should be a percent per unit time, so there really ought to be a year snuck in there. Okay, our book doesn't do that, and so they're not really trying to, quote unquote trick you. But the units down here and the units here have to match, because when I multiply that R and that T together, I'm going to have a year in my denominators and a year in my numerator. They have to cancel. Okay, many problems will tell you an interest rate per year, but then they'll give you the time in months or days or something else, and you have to do that extra conversion because it's got to be matching unit of years and years, so they cancel. Okay, in this case, our book doesn't even cover that subject, so we won't worry too much about it. Okay, but otherwise, there we go. The only unit that's going to be on the board is dollar signs for interest and dollar signs for principal. The years are going to cancel, so it looks pretty good here. So $94.50 equals some principal that I don't know, that's what I'm looking for, times my interest rate, which is 21%, times my years, which is 1/2 of a year. Okay? So it might be a little easier if we convert that to a decimal, a 0.21, and we could even make that a nice easy decimal, a 0.5. So there we go there. So let's take that 0.21 times 0.5. What do we get? We get 0.105. Okay. So 94.50 equals P times 0.105. Okay? That's my coefficient in front of P. It happens to be behind P, but it's P times some number. So I'm going to divide by that number. Both sides. So I need to take $94.50, 94.5. I need to divide it by 0.105. 900. 900 equals P, okay? And we can always turn it around and say P equals $900. So what are we saying? If I have $900 and I invest it in this account that pays 21% per year and I only have to leave it in there for a half a year, I'm going to make almost $100, $94.50. Okay, that's a sweet deal. All right, good luck finding that rate though. But that's how we would do a problem like that. Okay? Again, this is simple interest. Most banking accounts would pay a compound interest, and that's a little more complicated formula. Okay, good deal. Example 5 has got a really messy looking formula. Let me pull the book over. In the world of pumps and fans, fans maybe in particular, where you've got a belt-driven motor, means the motor is not what they call a direct drive motor, directly coupled to the shaft. It's off to the side. The motor has a pulley, and then your device, your fan, has a pulley, and there's a belt in between. If you've ever serviced any equipment like that, you kind of know what I'm talking about. There's two pulleys and a belt that goes in between them. Well, how do you calculate the length of that belt? Okay, it's a kind of complicated looking formula there. See that? Length equals 2c plus 1.57 parentheses big D plus little d plus a fraction of big D plus little d on the top divided by 4c. Look at all that stuff. Well, it's all identified what these dimensions are. Okay, the length is the length of the belt all the way around, the whole length of the belt. C is the distance between the two centers of those pulleys. Okay, and then the big D and the little d are the two pulley diameters. Okay, everything needs to be in inches for this formula. The formula doesn't really explicitly say that, but everything needs to be in inches for this formula to work out. And we're given everything in inches, so they're not really dwelling too much on the units with this problem, but just to drive the point home. So let me write it down. L equals 2c plus 1.57 times big D plus little d. Okay, then plus a fraction of numerator big D plus little d over denominator 4c. Okay, there's my formula. Now I am going to be told to round to the nearest hundredth, so we're going to get a decimal here. Okay, and again, if we just think about units for a second here, we're really not asked to talk units, but it's all got to be inches. C is in inches. So 2 times C will be inches. All these D's are in inches, so 1.57 times these D's will be inches. L is in inches. Here, this one term, though, it's really not explicitly shown. Maybe that's why they don't even talk about the units. My D plus D is in inches, but my C is also in inches. So it looks like the inches are going to cancel here, and I'll be left with no unit whatsoever. So there must be a hidden unit inside this 4. We don't know where this 4 came from, but the 4 must have a unit such that it would put an inch back on the top of this fraction and give us inches. Otherwise, we could not add inches plus something else. It wouldn't make any sense. So they all have to be in inches, okay? And again, we're not explicitly told how that all works out, but we're just told to stick with the value of inches, okay? So let's not dwell on that, but everything is inches here. We're told what C is. C is 24 inches. Remember, that was the distance between the two wheels, the two pulleys. This distance here to here was distance C. Okay? We're told what big D is. Big D equals 16 inches. Okay? That was the diameter of my big shaft here, my big wheel. So that's D. We're told what little d is. Little d is 4 inches. Okay, that's my little diameter there, okay, D. And then again, there's a belt that goes around both pulleys. All the way around, that's this L I'm looking for. How long of a belt does that need to be? Okay, there's my formula. Let's plug the information in. L equals 2 times C, so 2 times 24, and I'm going to drop the units, okay? The units are going to work out to be inches. 2 times 24 plus 1.57 times 16 plus 4 plus a big fraction here, 16 plus 4 on the numerator and 4 times 24 on the denominator. Okay, there we go. This is a big order of operations problem. Again, and when you get the hang of that order of operations, you see these plus signs are like the great separators. The last thing I'm going to do is add. So I've really got a problem here, and a problem here that I can kind of work simultaneously, because I'm not going to try to add them until the very end. Okay, now I'm just going to follow the book here and not go any further. This is example 5, by the way, if I didn't say that. Example 5. On page 380. I'll just follow the book here. The book does not take 2 times 24 on this first step, although you really could, but I'll leave it alone. 2 times 24 plus 1.57. Here I need to simplify this parentheses first. We'll call that 16 plus 4 is 20. And here I can start knocking away at my fraction here. On the top, I've got 16 plus 4 is 20. On the bottom, I've got 4 times 24, which we can call that 96, right? Okay, now let me go back and multiply. I'm going to get a 48 there, plus, if I take 1.57 times 20, I get 31.4. And if I divide that fraction there, 20 divided by 96, I get 0.208. And then the 3 starts repeating. 3, 3, 3, 3, 3, okay? Add those 3 numbers together. I'm going to get 79.608, and then again the 3 starts repeating after that. Okay, now we're asked to round in this problem. I didn't write it down, but the problem says round to the nearest hundredths. Well, that's that position right there, right? That's 0. It's either going to stay a 0 or turn into a 1. I make that decision by looking to the right, and I say, aha, that's 5 or bigger, so I'm going to bump it up. 79.62, again, the unit here was inches, so that belt needs to be 79.62, I'm sorry, not 62, 61. All this hard work, I'm making this video, and then I blow it at the last second. Bear with me. Okay, 79.61 inches. Okay, that's how long our belt needs to be. Okay, alright, in the next video we're going to start shuffling formulas around. We won't have all the numbers, just the letters, and it seems like it's harder, but you'll see it's really not that bad.